Okay, what I'm going to look at today is looking at some of the third generation photovoltaics and what are the critical challenges with them. It's been nearly a decade. Oops, where's the slide? Oh, there we go. It's been nearly a decade since they started to be heavily proposed and investigated. So if you look at, for example, for the third generation, if you look at the approaches under ideal conditions, so if you look at the thermodynamics or detail balance and put all parameters to their ideal, pretty much all the approaches can be shown to have the maximum thermodynamic efficiency of 86%. If you start including some of the more realistic assumptions into detailed balance, spectral selectivity, some of the fact that you can't take the band gaps to zero or to infinity, then what's actually interesting is that you find that a lot of the approaches have also very similar efficiencies, and they're about 50%. Now, this number right here highlights the challenges. If you look at the efficiency of approaches that or if you look at the efficiency specifically due to advanced concepts. So if you put quantum dots in a material, you'll get a certain efficiency just due to the material. If you try to extract out the added efficiency due to, let's say, multiple exciton generation or to an intermediate band, there is no structure that has demonstrated an energy conversion directly due to the advanced concepts. So again, that's not to say that none of the advanced concepts have all shown zero efficiency, but quantum dot devices are in a bulk material, and they'll all have some residual efficiency just due to the fact that they're in their bulk. But it has not been demonstrated that you can get an efficiency from any of these advanced approaches. So these sort of numbers highlight a couple of the challenges. First of all, this is lower than what you can get with some of the advanced tandem efficiencies. So if you're looking at this number and this number, then one of the questions is, why do you sort of want to use nanostructured, or why do you want to use third generation approaches at all? One of the reasons is that, or one of the potential reasons is that if you look at I think I missed the beginning of your talk, but you've probably shown this and talked about it. Okay. Well, maybe I'll skip that. Then, I'll go ahead and do it. So if you look at the experience curve, and you can tell me if this contradicts and if everybody falls asleep, I'm assuming it is exactly the same as what Dick said. This is the experience curve. Now, what you want to do is to be at obviously a low dollar per watt level. And if you start out with a completely new technology, so let's say you start out with a technology that's made from a material that nobody's ever heard of, you don't know how to make it. So for example, some of the intermediate band materials are modeled but don't have a good history of being investigated or being found. Then what you're doing at best, if you can solve all of these problems, then at best you're starting out here and you still have to move down the efficiency curve. Now, new technologies do have the ability to have a slight increase on the overall experience curve, but even the IC technologies couldn't maintain the more rapid experience curves over orders of magnitude of production. So pretty much the best you can do is to have a small, or over a short time frame or over a short increase in production capacity, you can increase the experience curve. So if you're starting out with a new material, then you have to go all the way down the experience curve until you hit the low PV module price. However, you're also stuck at the other end. Silicon and the thin films are on this experience curve and unless you introduce some kind of new technology, are unlikely to move from it substantially. This means that, I'll try and go through this quickly, but this means if you look at the total magnitude of the numbers of the total production capacity needed, by which time photovoltaics is a substantial fraction of the electricity, you're out somewhere at this green line right here. This is megawatt peak of production. So the standard curve intersection with the green line gives you a cost at about just a little bit under $1 a watt. Now that's a PV module price. The system price is roughly double that. And if you make a couple of assumptions, translate that intersection point into a cents per kilowatt hour, you're over, in good climates, you've hit grid parity. In poor climates, you haven't hit grid parity. So that this market right here is still relying on subsidies. And that could be a problem because of the large market size, that your subsidies need to be pretty large. So what you can do is you can use some of these advanced approaches, apply them to existing technologies, get a small jump on the experience curve, and then you can integrate some of the novel approaches which do have the potential to give you a jump on the experience curve, integrate them with existing technologies, and that is a potentially feasible way to accelerate the cost reduction of existing technologies. Okay, now that's sort of one of the ultimate goal of this, to apply some of these new technologies to existing technologies. However, before we do that, or before you can think about doing that, you have to understand what are the efficiency potentials of the technologies, which ones are worth looking at, and which ones are worth investigating. I put the sort of summary right at the beginning. So, and that's because if we look at, what I'll do is go through all of the different approaches, but I put the slide up here to highlight what the barriers are in each of them. So first, there are a couple of physical barriers. In most of the approaches, the interactions between the various particles in the system and how to control those interactions are not adequately understood. So in multiple exciton generation, for example, we'll see that there's still considerable still considerable controversy about the exact nature and if you don't understand the exact nature of the interaction, it's very difficult to optimize it. Another fundamental physical process is how to include transport. So that'll be a theme throughout all of the times when we go and look at the advanced concepts. What do you do about transport? Then another issue is, so these two are quite fundamental physical ones. Even if we understand the physics, we understand the physics in tandems, but that doesn't mean we can make an 8-junction tandem device. We still need to have materials in order to implement them, and that's not, for a lot of the advanced concepts, these aren't known. Then there are also two sort of more practical considerations. One is even if we do understand the physics, even if we have designed materials, how do we go about fabricating them? In, for example, the quantum dot approaches, you find that the desired size of the quantum dots is often in the nanometer range and requires close packed quantum dots, which is difficult to do. Now, luckily for solar, this is of interest to a whole lot of other areas. So solar isn't really the only one looking at this. And then the final barrier is that if you're looking at bulk materials, you generally find that the efficiency of a bulk material tends to be controlled by the defects in the bulk. And essentially the trade-off that everybody, or the optimization that everyone tries to do, is to maximize the quality of the bulk material given existing commercial costs. If you're talking about nanostructures, the bulk isn't that relevant, but your surfaces are very, very important. So in some ways it comes down to a practical problem. can you control bulk defects better, or can you control surface defects better? And if the answer is that you can control surface defects better or surface properties better than bulk, that is a huge incentive driving towards nanostructures and the advanced concepts. If it turns out that that it's easier to control bulk materials, then that's a very strong disadvantage. Okay, the high efficiency approaches are often thought to have been a very recent phenomenon, but they've actually been proposed or versions of them have been proposed and suggested for a fairly long time. So tandem, the first paper on a tandem is from 1955. Wolf in 1960 also proposed what could be considered a forerunner to the intermediate band approaches concerning defect levels. The impurity photovoltaic effect, which from a thermodynamic standpoint is indistinguishable from the intermediate band, was proposed in 1970. You can see fluorescent concentrators and hot carrier solar cells all near the early 80s. So there's been a long history of looking at these, but what has changed recently is that the physical processes in a lot of these suggested effects rely on the understanding and the ability to fabricate nanostructures. So that, for example, so that once nanostructures began to be better understood and better developed, then a lot of these effects right here also were able to be examined and better understood. A second driver for looking at all of these again is that a lot of the conventional processes are sneaking up on their efficiency limits. So the silicon record of 24.7 is not that far off the 26% practical efficiency limit. The tandem records have also been recently, they've been also increasing, and they're now over 40% and increasing by a couple of percentage points, a couple of fractions of a percentage point a year. But nevertheless, the sort of big jumps in efficiency are thought to be over, so people look for new approaches. A couple of comments on thermodynamic efficiencies, and one, and this slide is really sort of more of a touches on some of the notation and how it's used not only by solar but by other areas. For some areas, for example, let's say occasionally the bio or the biofuels folks will quote the Carnot efficiency as the relevant efficiency for the solar conversion processes. This is not the correct efficiency. The Carnot efficiency is the maximum efficiency which occurs at zero work. So, or not at zero, but as infinitesimally small work output. So if you are trying to actually make a power generation device, then the Carnot efficiency is only relevant in that it is the maximum efficiency above which you can never go beyond. It does not give you an idea of what an attainable efficiency is. And depending on the processes, there can actually be a fairly substantial difference between the Carnot efficiency and some of the others. Another efficiency that you will hear in solar is gradually being known as the Landsberg efficiency, which he published, I forget what year, in a very, very elegant one-page paper, derived the 93.3. And we actually went back and did the full derivation, and I think it ended up being like 20 pages or something if you don't take all the shortcuts. So a very elegant paper, did the 93.3. This right here is in some ways analogous to the Carnot efficiency. The Carnot efficiency not only has the problem that it is a zero work efficiency, but it also has the problem that the that the energy that you're considering is the solar flux minus the flux radiated back to the sun. And Landsberg correctly points out that solar cells do have very little practical impact in maintaining the sun's temperature. So rather than considering the total solar flux, the total energy, you just have the solar flux. Okay, so these two numbers right here are nice numbers, but this again is a efficiency at zero work. You can't get to it. If you have the solar energy efficiency, you have to take the efficiency at maximum work, not the maximum efficiency. You have to take the solar flux at input as an input, and if you do that, you get for a solar quantum, and I'll just explain what these are in a second, a efficiency of 86.8, assuming a certain spectrum and the Earth's temperature at 300K and stuff like that. If you assume a solar thermal process, then the standard calculation gives you 85.4%. These guys right here actually have quite different thermodynamic equations. For the solar quantum, you actually have a particle balance equation. Essentially, you have a photon coming in. That photon has to interact with electrons or other photons, or it has to interact with some quantum mechanical particle. Its energy is at that interaction either used or lost. You can't sort of, in solar thermal, you can give the carriers to some kind of pool that heats up, and you can extract as much or as little energy from that you want. But in this process right here, you actually have to use it or lose it. And the equations are a little bit different, and the physics is actually quite different of what you end up with. But I won't go into, I think you've already heard enough about thermodynamics, so we'll leave it there. Okay, so if we do the efficiency calculations, what do they tell us? First of all, that you should concentrate the sunlight. If you have a one-junction device, you get this is a black body, so it's lower than the AM 1.5 efficiency that you saw in Professor Swanson's talk. You get under one sun 30% maximum concentration, 40.8. It's not on the table, but it's an interesting number, that if you assume solar thermal or solar quantum, they respond hugely differently to concentration. So, for example, the solar thermal systems at one sun are around 10 to 13%, whereas under maximum concentration, they're already up near 85%. So depending on, this is for the solar quantum, and the concentration has a very, very substantial effect depending on what type of converter processes you're assuming. I won't talk about concentrators too much here. I think you may have already heard about them. The other thing you want to do is optically split the solar spectrum, and that's because there's no entropy penalty for splitting the spectrum. So if you're just purely looking at thermodynamics, there's a huge thermodynamic penalty for trying to convert a very wide spectrum range, but there is no thermodynamic penalty for splitting the light up into its component parts. So the standard way to do this is just with a tandem solar cell. And out of all the third generation concepts, tandems, and actually tandems object to themselves being called third generation, but there you go. So unfortunately, nobody's been able to come up with a good name for the advanced concepts or stuff like that, or the third generation that doesn't include tandems. Now, and I won't focus on tandems that much either. The efficiency of the tandems is largely controlled by the need to have ideal bandgap materials for however many junctions you have. The other thing that the efficiency calculations do is that there's actually a relatively small number of assumptions that go into detail balance. And so the other way to get a higher efficiency is to beneficially circumvent one of those assumptions. And there's actually not that many of them. Okay, just because it is third generation, so third generations are the first of the practical third generations. Presently, the devices being used in concentrators are at 3 junctions, and they have a theoretical 1-son efficiency of 56. Under maximum efficiency, they've got a efficiency of over 60. However, that the present generation of tandems can't reach this efficiency because of a variety of reasons. The band gaps aren't ideal. The voltages are below what detail balance tells you. So really there's a substantial amount of research in the tandems looking into just optimizing the band gaps, how to grow in lattice mismatched, and also looking at new materials. What I want to focus on a little bit more is on what are the other third generation concepts and what are the barriers to them. So I'll just briefly mention from this table that even though there's a huge number of approaches that people have looked at in terms of the advanced concepts, but in terms of, if you look at it from a thermodynamic standpoint, there's actually only a relatively small number of assumptions that go into detail balance. So all the approaches have to address one of these 4 assumptions that go into the detail balance. This one right here is actually a pretty interesting one. But if you want to assume non-equilibrium thermodynamics, then you have to go to substantially different types of calculations. And not only that, the devices are quite, well, they assume that the size scale you'd need is better than terahertz. So I'll talk about these 4 assumptions. I'll leave this one off, partly because the calculation approaches and the processes are even less well understood than these. Okay, so let's go back here. So detail balance assumes that your input is the solar spectrum. Clearly, you can split that optically, but there's no reason to assume you're splitting it optically. You can also split it with some kind of conversion process. If you split it with a conversion process, you now get a thermodynamic penalty, but nevertheless, this is an assumption. You can transform the spectrum and get an efficiency benefit. These 2 right here are quite similar, or I shouldn't say similar, but related to each other. In some ways, they're inverses of each other. Detail balance assumes 1 photon gives you 1 electron-hole pair. You can circumvent that. On the other hand, related to this, detail balance assumes that if you have 1 photon, it goes across 1 quasi-Fermi level separation. And if you are circumventing this, then there's no need to assume a single quasi-Fermi level separation, so you can have multiple quasi-Fermi level separations. Detail balance also assumes a constant temperature, that the Earth's temperature is equal to the cell temperature is equal to the carrier temperature, and there's no reason to assume that either. We'll get to this in a little bit. This is actually an interesting one because this is actually a hybrid between the thermal converters and the quantum converters. Okay, so for what we're doing in multiple spectrum approaches is we transform the incident spectrum into something that has the same power but has a narrower wavelength range. One of the biggest approaches, or one of the approaches that's been suggested to do this is called thermophotonics. Now, I actually should mention that the key advantage of the whole sort of multiple of transforming the spectrum is that you can use existing solar cells. So, or you can, if you tune the spectrum right, you can just use existing solar cells. You do all the interesting physics in optical processes. This has the advantage that you don't need to transport the carriers. So you have light in, you get light out, and you never have to worry about some of the effects like particularly like transport. So an example of this is where you heat up, for example, you heat up an LED right here with the sunlight. The LED emits light. The light emission from an LED is, of course, narrower than what you get from the solar spectrum. So you shine this LED light onto, let's say, a standard silicon solar cell, and you then have a higher efficiency process for your silicon solar cell. The interesting physics in here is related to the fact that in an LED and in some other devices, you're relying on getting optical, or just you're not relying, but you utilize the fact that you can achieve to some kind of optical cooling. So if you bias an LED, you certainly bias an LED below its band gap, but it emits at its band gap. So it's utilizing some of the thermal energy that it has and transforming that into light. So the trade-off, of course, here is that you have to power the LED, and that has to be done by the solar cell. So you have to take that into account in your realistic efficiency calculations. And if you go through and if you model this stuff, you find that the efficiency depends on the band gap of the solar cell, the band gap of the LED, the temperature of the LED. So clearly the hotter the device is, the more thermal energy you have. The bias of the LED, so if you go to a higher power density, then you are going to have a more efficient solar cell, but you're also going to be extracting less thermal energy from the LED itself. And of course, if you have non-radiative recombination, then the overall process is extraordinarily sensitive to non-radiative recombination. You're trying to convert the incident sunlight into light. If your LED has non-radiative recombination, you're converting it into light and heat. What you end up with is that if you put all of these in, if you assume, let's say, a silicon solar cell, then you will find that, here's the numbers, that the net effect is that you get an efficiency of roughly a practical, or I shouldn't say practical, but a realistic thermodynamic efficiency of around 50%. So the thermodynamic efficiency that, so it's still an ideal efficiency, but you might be able to, if you do everything right, start to approach 50% in that. If you put in additional losses, such as non-radiative recombination, and if you run these things at a higher carrier concentration, even the radiative materials start to have Auger combination, start to have Auger recombinations or other non-radiative losses, then you start to get efficiencies around 33%. And then overall efficiencies of around 33%, which, and these two numbers start to approach the numbers you can achieve with some other techniques. And so even though it is, from a physical standpoint, an extraordinarily interesting physics, trying to control the carrier interactions such that your photon and or particularly you're trying to control your electron, photon, phonon interactions, from a practical standpoint, you're looking at only moderate efficiency gains. Of course, there's always a way to claw back efficiency if you stick in a couple of more approaches into the thermodynamics. In this right here, for example, you split the spectrum, use a regular solar cell for the very high wavelength light, which a standard solar cell converts well, and use the low energy light in this type of thermal process. This claws back some of your efficiency and gets you back up to about 50% or so. But again, I guess the central theme is that if you want to do it, you have to understand the interactions and be able to control the interactions between, in this case, the photon, electron, and phonon. Now, the phonon, from a detailed modeling standpoint, modeling the electron-phonon interactions actually requires some advanced simulation, and it'll show up as a theme in just about all of the other cases as well. There are two other, or one other set consisting of two approaches that you can use to convert the spectrum to a narrower spectrum, and that's up conversion and down conversion. I won't spend much time on them because from a thermodynamic and also in some and from a more practical standpoint, these are thermodynamically identical to either the MEG approaches or to the intermediate band approaches. The only difference is that because you extract the carriers out as light, you actually really don't have to worry about transport in this case. Whereas in the multiple exciton generation and intermediate band, you don't worry about transport, but there's always a little note at the bottom. Yes, eventually we'll have to worry about transport at some point. Okay, so for up conversion, I'll just explain why this is essentially, again, identical to a intermediate band process. If you want to make this efficient, you need to have what amounts to a quasi-Fermi level here, here, and here. This is interesting because if you do get an intermediate band material working, it will be not just of interest as a solar cell, but also as an extraordinarily efficient phosphor material, which has applications well beyond photovoltaics. I think that's not really 1 o'clock, is it?
We started a little late, so you can...
Okay, so, okay, give me a couple. Okay. The other, or the second sort of class of approaches is where you get around the Shockley-Queisser limit of having one photon giving you one electron hole pair. You can do this in either way. One photon gives you one high energy photon gives you 2 or more electron hole pairs, or you can do 2 photon gives you 1 electron hole pair. Now, one comment about this. This is actually, from a physical standpoint, substantially different than the intermediate band stuff. So this is right here has to be a coherent process if you're not going to put an extra energy band or an extra quasi-Fermi level in. This process right here, there's some experimental evidence that it occurs in nanostructures, but in general it occurs with much less efficiency. So nearly all of the focus is on looking at this process right here, where you have one high energy photon giving you multiple electron hole pairs. It goes by a whole lot of names: Auger generation, impact ionization, multiple exciton generation, multiple carrier generation. And those multiple names really reflect the fact that it has been proposed to use a variety of physical processes. If the effect of impact ionization or Auger generation is known in bulk materials, people in bulk materials have even shown on a quantum efficiency that you can get an increase in the overall, that you can get, actually that's a little bit, that you get a that you can get a quantum efficiency greater than 1. But the effect is relatively small in bulk materials, and the dominant effect occurs in nanostructures where you don't have to, or where the conservation of momentum rules are relaxed. So if we're modeling the effect theoretically or ideally, then we have these curves right here. For this is no multiple exciton generation. This assumes that you have a maximum of 2 electron hole pairs generated for a high energy photon. This assumes 3, so on and so forth. What you find is that for a large number of electron hole pairs generated, you quickly move down to a relatively small band gap. if we now start to put some non-idealities in it, we find that the threshold energy is not, rather than using M, let me explain it with an example. So if you have a photon energy of twice the band gap, then for between 2 eG and 3 eG, you should be generating 2 electron hole pairs. But it turns out that in practice, that's not quite true. Rather than being M times the band gap, there's actually a threshold energy greater than MEG. So to generate 2 electron hole pairs, this might be, let's say, 2.5 times the band gap, and the next process only starts at 3.5 times the band gap. So this reduces the maximum possible efficiency that you can get out of the process. The other non-ideality that you need to include, it relates to this large M right here. So M is the maximum number of electron hole pairs that you can get out. Theoretically, you can take M out to infinity. It has relatively small impact, particularly under AM 1.5, where you don't have many high-energy photons. But in practice, the maximum M that you see is going to be limited by the maximum quantum efficiency that you get. If you put those non-idealities in, you come up with a band gap that is actually much higher than, well, I skipped through this. This is the results of all the modeling. If you go out all the way to M equals infinity, you'll find that you get very, very small band gaps. If you put some of the non-idealities in, you find that your ideal band gap starts to go up. What's actually interesting is that silicon gives you 90% of the maximum efficiency. This is a little interesting because it means that you can start, that it's potentially relevant to the existing materials. The next uncertainty, or the multiple exciton generation out of all the approaches, has by far the best experimental demonstration of the physical effect. But even with the multiple exciton generation, there is a substantial amount of controversy, both regarding the magnitude of the effect and the modeling of the effect. So initially, there were reports of the multiple exciton generation up to about 700% quantum yield. But generally, people have been backing off on the very high measurements or the very high reports, and a more realistic or a more accurate number, I shouldn't say realistic, a more accurate number tends to be that your quantum yield is, well, this is actually a quite old result, but the quantum yield tends to be in the range of somewhere between 200 to 300%. This is, in some cases, or the variation in the measurements for the quantum yield highlights another one of the sort of themes that we keep talking about, and that's that the inability to repeat the results and the large variation in the results themselves has been attributed to the surface preparation and of the module, of the quantum dots, and how the surface physics changes as a function of time. Another uncertainty in the MEG devices is that there's considerable controversy in modeling the specific electron hole photon interactions that are necessary to demonstrate it. So it's uncertain whether it needs to be a coherent process or not, and particularly coming out of NREL, you'll see papers saying, yes, it needs to be a coherent process, or no, it does not need to be a coherent process. So again, even though this is the best of the experimentally demonstrated ones, there's uncertainty in how to optimize the exact nature of the electron-photon processes. And this, of course, then also hinders, if you don't understand what's causing the interaction, it hinders the ability to design materials to optimize it. The last, the last one I'll spend a little bit of time on is the multiple quasi-Fermi level. I've titled this the multiple quasi-Fermi levels because there's actually the intermediate band is by far the best known out of these approaches, but nevertheless, any structure that gives you a multiple quasi-Fermi level, regardless of if it's a band, regardless of if it's an intermediate band, can be used to give you an efficiency increase. One of the similar to what I said earlier about the phosphors, one of the interesting features of the multiple quasi-Fermi levels is that it can be used as the basis, or since you're designing new physical properties, these new physical properties have utility well beyond solar. So, for example, if you model the optical absorption coefficients of this material right here, the optical absorption is highly, highly nonlinear, and not only that, is also optically tunable. So if you shine a specific wavelength on it, what you essentially do is saturate one of these emission channels or absorption channels, and you then collapse one of the absorption mechanisms. So basically, it's useful not only for solar cells, but both the optical and electrical properties of this are nonlinear, tunable, and can be utilized in a range of devices. The advantages of this for solar are that for a 3-level structure, you get an ideal efficiency of 63.2. This is nearly identical to a 3-junction device, and that is no accident. That is because detail balance, in effect, you don't care how many band gaps or whatever you have. Well, you do care, but assuming that you have the same number of band gaps as you have quasi-Fermi levels, the detail balance is controlled by the number of quasi-Fermi levels that you have, not by anything else. So here you have 3 quasi-Fermi level separations, gives you the same thing as a 3-junction efficiency. If you put in another quasi-Fermi level in here, it gives you essentially a 4-junction efficiency. That's not, the numbers to sort of the first or second decimal point don't work out exactly, because if you have an independently connected tandem, you have a couple extra degrees of freedom, but nevertheless, that's sort of in the noise. So if this is essentially identical to a 3-junction tandem, what advantages do you get? Well, first of all, you only need 1 material rather than 3 to do this. You're also a little bit less sensitive to the material choice in this. However, this type of modeling assumes generally that you have ideal assumptions in detail balance, which is not necessarily true. In particular, the intermediate band will not obey spectral selectivity. So in a tandem, you actually have pretty good spectral selectivity. The top band gap takes out the top photons. There's very few high energy photons available to the low band gap material. That's not true in the intermediate band. It's perfectly possible for the low band gap material to absorb a high energy photons. And if you model it, you find that it makes very little difference. That this right here, I won't go through the details, but this right here is this curve right here is the curve with spectral selectivity. So you find that it's a relatively slowly varying function. You lose about a couple of absolute percentage points. What is a big, big, big deal in the intermediate band, and the reason that there has not been a convincing experimental demonstration of it, is that detail balance assumes you have ideal absorption coefficients, and that this is just absolutely not true in any type of the realistic materials you looked at. You'd think that we could go into the system and model and come up with a quantum dot system that has ideal absorption. That has also not been the case. An ideal absorption coefficient would look sort of like this, except that the 3 bands, that this edge touches that edge. If we go and model practical quantum dot systems, we have not been able to find a material that gives us that. So for example here, wherever there's a gap, we're not going to absorb photons. Right here, there's an overlap in what one material absorbs compared to another. This is a horrible absorption coefficient. It has all sorts of problems with it. You don't absorb and you overlap. So when you actually try to even do detailed balance modeling with realistic, or again, I shouldn't use realistic, but somewhat realistic absorption coefficients, you find that that we have not yet been able to identify a material that gives you the absorption necessary to get an ideal intermediate band. The other problem is it's actually a very, very sensitive function to this. If you don't tune your absorption coefficients, it's not that you get a little bit of current mismatch here and there, but you cannot maintain, particularly assuming a finite density of states in this band, you can't maintain a steady state absorption, and the efficiencies essentially just collapse down to, well, here's the efficiency as a function of the density of states for as good as for one case. So you can maintain about 30%, which is well below the 60%. Then the efficiency collapses if you don't have all your processes tuned. We would, it would be wonderful if you could go backwards and say, this is the absorption coefficient you want, give us the materials, but unfortunately that's not where the modeling is at the moment. Now actually one of the EFRCs is actually on this exact problem, figuring out here's the properties, how do we get the material, but at the moment we just have to go and try this material, make a quantum dot out of it, model the stuff, and then see what we get. Despite the fact that, despite the fact that people have not identified an ideal material, there's some experimental evidence for it. This right here is from Marti and Luque, where they shine IR light on a quantum dot sample and measured an increase in the photocurrent. Now, the reason I say that this is not an unequivocal demonstration of it is that what you need to demonstrate is multiple quasi-Fermi levels. And in order to demonstrate multiple quasi-Fermi levels, the processes have to be similar orders of magnitude. So you can actually demonstrate that you can achieve a small increase in the current, a couple orders of magnitude lower, without having multiple quasi-Fermi levels. So this is a very, very important indicator that we are getting something from the intermediate band, but it is not a demonstration that you have multiple quasi-Fermi levels. Another important, and this is actually a relatively old demonstration, is from Keith Barnum's group, that they modeled the photoluminescence and found that in order to fit the photoluminescence, they needed to use a lower quasi-Fermi level in the well than they did in the barrier. Again, that's indicating that there's something going on in the well and at the interface, but again, nobody has yet experimentally demonstrated that there are 3 quasi-Fermi levels at a simultaneous position. And then again, just tying that back to the modeling sort of can explain why. Most of these systems, if you run it through the models, you wouldn't expect them to show a quasi-Fermi level because the absorption coefficients are so poorly tuned. So the critical barrier for the intermediate band is also just if we could predict the interactions better, then then you could identify a material or optimize a material, and you might start thinking about making solar cells out of it. The last one I'll talk about, and I'll just do this very briefly, is the hot carrier solar cells. So in a hot carrier device, you absorb a photon. This electron interacts with other electrons such that all the electrons have the same temperature, but you extract it from the device before this electron interacts with the lattice. So basically the electrons or the holes are thermally equilibrated with each other, but not with the lattice. This right here, in order to extract it out, you need a selective energy contact, and this guy should actually be up there. You need a selective energy contact. What the advantage of this is that this essentially approximates a thermal converter, and with one slab of material, you can get a theoretical efficiency of 85% out of it. So this is substantially higher than out of any of the other approaches. People have experimentally shown selective energy contacts, but the collection times for these need to be on the order of femto or picoseconds, such that they need to be thin, and basically they face a lot of quite practical problems. You can combine the hot carrier devices with a quantum converter, where part of it acts like a thermal device, part of it acts like a quantum device. And because of the different response of a thermal converter to a quantum converter, you can actually, at finite concentration levels, get a higher efficiency out of your hybrid than you can out of either a quantum or a thermal converter. So this is, I guess, these type of approaches have some of the least investigated, and this is because they require a quite good ability to model not only electron interactions with each other and with photons, but also you have to start to model accurately all the phonon interactions. And that basically gives you just a whole nother level of complexity in the detailed physical modeling. Okay, so what then, as a summary, you have essentially three limitations to the third generation. First of all, and the most fundamental one, is the physical mechanisms. In none of the physical approaches is there unambiguous physical modeling of it. You cannot say, here's a material, here are all the physical processes, and this gives me an efficiency. So a while ago, sort of the concept of band gap engineering became popular. But what we're really looking to do here is to design the interaction between the carriers. We don't so much want to design the band gaps or engineer the band gaps, but we want to be able to tailor the interaction between the carriers from something a little more sophisticated than band-to-band or auger. And then, of course, I didn't mention it specifically in each approach, but the transport, once you have these carrier interactions, the transport mechanisms are much more difficult than they are in a standard bulk material. I sort of went over the fabrication processes at the beginning. So what type of nanostructures? If you're talking about quantum dots, you need extraordinarily small, closely packed quantum dots, which are not exactly known how to achieve it. Quantum wells are generally less interesting because they have a reduced modification of the density of states compared to a quantum dot or a quantum wire. Quantum wires generally will give you a sort of better optimum between having the difficulty in processing quantum dots but still getting the ability to transport it. And again, issue that is largely, again, is substantially ignored in a lot of these is that they are very, very highly controlled by the surfaces. If you want to measure anything, you have to pay attention to the surfaces, and you have to passivate the surfaces extraordinarily well if you're trying to get to the physical effects. Okay, that's it.